All right, so section 7.1 is on polynomial functions. So we've dealt with polynomials most of the time last semester. I mean, I think you guys are pretty familiar with polynomials. Okay, so a polynomial of degree n, so basically that's the highest degree in one variable, so we're only going to talk about one variable in this chapter, will look like a number times x to some power plus a number times x to one less than it, and so on. The numbers out front are called coefficients. The leading coefficient is not 0, and n is not negative. Like you can't have your degree be negative. All right, so state the degree and leading coefficient of each polynomial in one variable. If it's not a polynomial in one variable, explain why and do not find the degree or the leading coefficient. So number 1, so I have 7z cubed minus 4z squared plus z. Okay, so is it a polynomial in one variable? Do you think? Yeah, there's only one variable, right? And we didn't have a negative exponent, so yes. Its degree is the highest exponent, so the degree is 3. And the leading coefficient is the number out front. So see, notice how it's in descending order, like I had 3, 2, 1 for my powers. So my leading coefficient is the number out front, so it's 7. Okay, number 2. Is this a polynomial in one variable? No. Okay, so then we don't talk about the degree and we don't talk about the leading coefficient. All right, how about 3? No. Okay, so 2 wasn't because there was A and B. And then 3 wasn't because you had C to the negative 1. You can't have a negative exponent. All right, how about 4? Yeah, there's one variable, right? Your degree is 4, so that's the highest degree. What's the leading coefficient? 1, right? So you're basically thinking of rewriting this in descending order. So y to the 4th minus 3y squared plus 9y. So your leading coefficient is the number out front. So there was basically a 1 there. So 1 is your leading coefficient. It's just the number in front of the term with the largest degree. All right, so graphs. So some of these you remember. Remember how we did like our math aerobics? So we kind of know the shapes for these things. So like y equals x. What does y equal x look like? Yeah, Kern? It's just a straight line that goes right through the origin. It makes like a 45-degree angle, like that. Okay, hopefully you guys remember y equals x squared. What shape is that? Parabola, right. You even pronounced it correctly. You didn't say parabola. All right, and then y equals x cubed. Anybody know that one?
Is it like that?
I always call it the snake shape. I don't know. Looks like a snake like slithering in the grass to me. I don't know. Okay, so these are the most basic type of those functions. So basically if I had a y equals x squared and then I had some other stuff, 5x minus 4, that's still going to be a parabola shape because the largest degree was 2. Okay, so it's still going to look like a parabola. All right, now for some other ones. Now y equals x to the 4th might be a little bit harder. You can do a t-table if you want. What it ends up being is very similar to y equals x to the 4th. So it's going to be very similar to y equals x squared, except it's going to be more flat. Oh, mine's kind of weird. So it doesn't cross the axis there. Mine kind of looked like it did. Let me try it again. So it's going to come down and it's going to kind of flatten out. It's not going to be flat there. It's just going to look flat. And that's between 1 and negative 1. Okay, so let's kind of think about what the t-table does. So let's think about y equals x squared versus y equals x to the 4th. Okay, so at 1, y equals x squared, if I square 1, I get 1, right? So I'm having the point 1, 1 on both of them anyway, like y equals x squared. So I have the point 1, 1. Okay, same with negative 1. If I square it, I get 1. If I raise it to the 4th, I get 1. Okay, think about bigger numbers. If I had 2, 2 squared is 4. What's 2 to the 4th power? 2 times 2 times 2 times 2. 16. All right, so basically if I had 2, it shoots up really fast to 16. But on the parabola, it was only at 4, 2, 4. Okay, so it got steeper really fast. And then let's think about fractions. If I had 1/2, 1/2 squared is 1/2 times 1/2, which is 1/4. What's 1/2 to the 4th? Yep, 1 over 16. Okay, so that's even smaller than 1/4, much smaller than 1/4. Okay, and that's why it flattens out along here. So at 1/2, it's so close to the axis, much closer than this one. Does it make sense? Okay, so basically if I have x to the 4th and even x to the 5th, it's going to flatten out between -1 and 1. So x to the 5th ends up looking like x cubed, but between -1 and 1, it gets closer to the axis. Crosses there. So it's kind of flat along there. Make sense? Same thing for x to the 6th, x to the 7th. Okay. Okay, so last semester we talked about how to sketch the graphs of f of x equals x minus 2 squared and g of x equals x squared plus 7 with transformations from earlier sections. Do you guys remember the transformations? Okay, so if I had x minus 2 squared, remember if something's inside with the x value, so it's in the parentheses, it kind of does the opposite of what you would think it does. So when I think of moving the x value -2, when I see -2, I think I would go left 2, but it really goes right 2. This one went right 2. And this other one, x squared plus 7, what did it do? Up 7, right? So it looked like the normal x squared, but it was up 7. Okay, so number 1, so sketch the graph of f of x equals -x cubed plus 2. Okay, so I said x cubed looks like this shape here. Okay, what about the negative? It reflects over the x-axis. And what about the plus 2? Up 2. Okay, so we put those all together. So so here's the first one. You don't have to draw these. So that's what normal x cubed looked like. Then I reflect it over the x-axis. Then you go up 2. So your final answer should look something like that. Make sense? Okay, what if you've forgotten the transformations? What's another way you could know what this graph looks like? What could you do? How did you graph before you knew transformations? Yeah, just use it like a table of values, a t-table. Okay, so this next one, so I have -x squared. So first of all, x squared looks like this. -x squared flips it over the axis, and then you go down 4, right? Okay, so this one ends up looking like this. Okay, so we're going to talk about end behavior. So end behavior basically tells you what happens on the very ends of your polynomial. Okay, so maybe you might have both of the ends pointing up, both of them pointing down, right? Like number 2, both of them pointed down on the end. Maybe like an x cubed where one goes up, one goes down. Okay, so that's going to tell you what's happening basically as your x values go to positive and negative infinity. So what's happening on the very right side as you go to positive infinity, what's happening on the left side as you go to negative infinity. Okay, so if I have odd degree, so what's the most basic one that you've learned that has odd degree? Well, besides y equals x. Yeah, x cubed. Okay, so that's what we're thinking of when I see the polynomial has odd degree. Think of x cubed. Okay, the leading coefficient is positive. So this would look like y equals positive x cubed. If the leading coefficient is negative, we're going to look like y equals negative x cubed. Okay, so any odd degree with a positive leading coefficient, the ends are going to look like y equals x cubed. So when I talk about the ends, think about what y equals x cubed looks like. Do you guys have it in your head? It looks like this, right? Okay, so that means on the very ends, you're going to go up on the right and down on the left. So this is for anything that has odd degrees. So the highest degree is odd, and that leading coefficient is positive. Now, it could be going up and down, up and down. We don't know what's happening in the middle. So I'm just going to do like a dotted line in the middle. Oops. But we know that the ends are definitely going to look like that. Okay, that's what it means for end behavior. Okay, I'm going to show you kind of a weird way to write this. It's going to be confusing at first when you learn it, but it won't be bad. Okay, so think about, we say as x goes to infinity. So x arrow infinity. Okay, that means as your hand goes further to the right, as your x values get bigger and bigger and bigger. You following me? What's happening to your y values? Are they getting bigger or smaller? Bigger, yeah. So we're going to say as x goes to infinity, y goes to infinity. Right, so as I go to the right, my end is going up. Okay, for the other one, I say as x goes to negative infinity. So that means as I go to the left, right, as my y values are getting, or as my x values are getting negative. So what's happening to y values? They go down, right? So the y values are getting negative. So we say y goes to negative infinity. Make sense? Okay, so let's talk about the other one. So if I have y equals negative x cubed, what's different about negative x cubed than x cubed? Yeah, it flipped over the x-axis. So it's going to look like, the ends are going to look like this. And then, again, we don't know what's happening in the middle. It could bounce up and down, up and down. Okay, so let's talk about the ends on this one. Okay, so let's talk about the right side first. So as my x values get big, so as x values go to infinity, do you understand that part? What happens to the y values? Yeah, y goes to negative infinity. So basically think about a point that would be on this end. That point would have a positive x value and a negative y value. That's basically all we're doing. We're saying as you get positive for x, your y's are getting negative. Okay, this other side, we say as x goes to negative infinity, so as my x values are getting negative, y goes to, which one? Positive infinity, right. Okay, makes sense? Okay, so let's draw these other two. So the next one says the polynomial has even degree and the leading coefficient is positive. So think of the most basic thing with even degree, leading coefficient is positive. What's it going to look like? Y equals x squared, right? And y equals x squared, its ends go like that because we know it's a parabola that goes upwards. Okay, so any even degree with leading coefficient is positive, the ends are going to look like that. Now in the middle, like I said, you could have it going up and down, up and down. We don't know what's happening in the middle, so I just draw like a dotted line in the middle. Okay, so let's start with the right side. So as x goes to positive infinity, y goes to positive infinity, right? Again, think of like a point on this end. It would be positive, positive, right? Positive x value, positive y value. All right, on the left side, I say as x goes to negative infinity, now what happens to y? Positive infinity, right? And this is where people always make up, or they make mistakes because they think they should go opposite. Like the y's should be different. Like one should be positive, one should be negative, but not on an even one, right? They're both going to be the same for the even one. Okay, so leading coefficient is negative. This is going to look like y equals negative x squared, which we know is a parabola going downwards. So the ends are going to look like that. Okay, so I say as x goes to infinity, y goes to negative infinity. And the other one I say as x goes to negative infinity, so as I go to the left, y goes to negative infinity. Okay, this is a very like calculus type thing that you're learning. You'll do this a lot in pre-calc too. Okay, we good on those? Okay, so let's talk about these ones. So it says identify the leading coefficient, the degree, and now we're going to talk about the end behavior too. Okay, so the leading coefficient, it's in that descending order. So my leading coefficient is -1, so it's negative. My degree is 4, so it's even. Basically just circle that first term and think, does it look like negative x squared, negative x cubed, positive x squared, positive x cubed? Which one does it look like? Negative x squared, right? So your end behavior, usually I just have people draw the end just to make sure. So your end behavior is like that. And on your homework, I try to write like as x goes to positive infinity, and then I have like a blank. And I'll say as x goes to negative infinity, and then I'll have a blank. Okay, both of them are the same in this case, right? So are they positive or negative infinity? Negative infinity, right? So we're going to say y goes to negative infinity and y goes to negative infinity because they're both going down. The y values are getting smaller. Okay, you guys try B. Try B. Okay, so your leading coefficient was 2. All right, so it's positive. And your degree was 5, so it's odd. So think of the most basic positive odd. It's going to look like positive x cubed. So your end should look like this. All right, so I would say something like as x goes to infinity, and then I'd leave a blank for you. So as I go to the right, so as my x values get bigger, so as I'm going out along here, my y values are going up. So I say y goes to positive infinity. Okay, and as I go, as x gets smaller, so as x goes to the left, y goes to negative infinity. So those are the answers. Okay, so number 2, I think these ones are kind of easier. Okay, so is this going to have an odd or even degree? So 2a. Curtin, what do you think? Odd, because they're going in opposite directions, right? The ends. Okay, so it's odd. Okay, now the next question is, does it look like positive x cubed on the ends or negative x cubed on the ends? Negative, right? So it's odd and negative. All right, how about the next one? Victoria, what do you think on B? Even, because they're both going in the same direction. And is it positive or negative? Uh-huh. So even and positive. Good, because the ends just look like positive x squared. Okay. So that's going to help us as we graph polynomials. So we've learned how to graph like parabolas. You know, we've done t-tables and things. Now we're going to do harder things, polynomials. Okay, so we're going to kind of follow some of the same steps we've followed before. So you're going to find the real zeros. Do you guys remember what zeros are? So zeros are x-intercepts, where it crosses the x-axis. And we do that by setting y equal to 0, right? X-intercept set y equal to 0. And then the y-intercept. So y-intercept set x equal to 0. Okay, so let's find the x-intercept. So the zeros and the y-intercept. So the y-intercept's the one that's real easy. You just plug in 0 for x. So it'd be y equals 0 cubed minus 0 squared minus 4 times 0 plus 4. It's always that last number. So at 4, 1, 2, 3, 4, I'm going to cross the y-axis. The x-intercept's harder because you set your y equal to 0. So it's 0 equals x cubed minus x squared minus 4x plus 4. Does anybody remember how we solved these? No? Can we factor? We can factor. It's a special way, though. What's it called? Yeah, it's factor by grouping, right? Split the middle. So we're going to split it down the middle. Okay, so on the left side, I pull out what I have in common. So if I have x cubed and x squared, they have x squared in common. And on the inside, I write what would be left if I pulled out an x squared for both of them. So I would need an x minus 1, right? Think of multiplying the x squared back in. You'd have x cubed minus x squared. That's what we wanted. Okay, now the next one, I know I want to have that same thing, that x minus 1 left. Is there anything that I can pull out so that I have x minus 1? Yeah, negative 4. Okay, so now we're to the point where we have like x squared times something minus 4 times something. You don't have to write this down. Okay, and that something is the same, so now we factor it to the front. So if I had factored just the y to the front, it'd be y times x squared minus 4. That's what we're doing down here as well. We're just pulling what they have in common to the front. So they have x minus 1 in common. So I have 0 equals x minus 1, and then I write what's left. So I'd have x squared minus 4 left. Can I go any further? What about x squared minus 4? I heard someone say it very quietly. X plus 2 times x minus 2. Okay, so now you can solve, because now you have 3 things that are multiplied together and make 0. So you could have x equals 1, x equals negative 2, or x equals 2. You could set each piece equal to 0 and solve. X equals 1, x equals negative 2, x equals 2. Okay, so those are your x-intercepts, or zeros. Okay, so that's where it's crossing the x-axis. So I have 1, 2, and negative 2. Okay, polynomials are always what we call smooth and continuous. They're always curvy. So a lot of people, when they get this, they're like, oh, I got it, and they just draw a straight line across. It's never going to do that for a polynomial. It's always going to be like real curvy and smooth. Okay, no sharp corners or anything. Okay, so can you kind of see where we're going with this? Okay, let's think about the end behavior. Okay, end behavior. So that's what we just learned. It's going to look like y equals x cubed, because my leading term is x cubed. It's odd and positive. So on the ends, you're going to look like this. Okay, so we draw those in. Okay, you could always plot some more points if you need them. And then number 6 says, do any of the x-intercepts have multiplicity? We'll talk more about that later, but basically, is there a value like for your x-intercept that was listed twice? Like, see how I had 1, negative 2, and 2? If I had one that was listed twice, like x equals 1, x equals 1, 2, then at 1 it's doing something special. At 1 it would come in, and it would hit it like a parabola and then pop back up. Okay, but we'll see those later. Okay, so when I sketch the graph, I'm going to come in, I'm going to hit the x-intercept, go up to the y. Now that isn't necessarily like the maximum. There's not going to be like a hill right there, you know. It could go up higher. We don't know. You could always plug in 1/2 and see if it goes any higher. Then it goes down and then back up. Okay, so that's our graph. Make sense? You guys think you could do that on your homework? It's not too bad. Okay, so let's try this one. This is the last one. Nope, I guess I'm wrong. All right, so f of x equals x to the 4th minus 5x squared plus 4. Okay, so let's find the x-intercept, the y-intercept. So the y-intercept's easy. Remember, plug in 0 for x. So what do I get when I plug in 0 for x? Y equals 4. So that's where it's crossing the y-axis. X-intercept's harder, so I set my y value equal to 0. So I have 0, because f of x is your y value, right? So I get x to the 4th minus 5x squared plus 4. How do I solve this one? You can factor, but what's kind of different about it? Melvin, do you know?
Is x cubed not there?
Well, it wouldn't be x cubed, but you're close. Let me help her out. See how if you had x squared and x squared? That would multiply to be x to the 4th. And then your outer and inner would be x squared terms, so they would combine to be an x squared term. All right, how about my numbers? What do I need?
1 and -4.
Yeah, I need -1 and -4, both negative, so that they multiply to be +4. Okay, so you're kind of foiling in your head to check. So first terms make x to the 4th, outer is -4x squared, and inner is -1x squared, so those do combine to be -5x squared. And then -1 times -4 is 4. Okay, so that's good. This one goes further. So I'd have x plus 1 times x minus 1 times x plus 2 times x minus 2. So if I set each piece equal to 0 and solved each one, you would get x equals -1, x equals 1, x equals -2, and x equals 2. So I have 4. Kind of a little hint, if you have a degree 4, the most you can have is 4. Okay, so I have -1, +1, -2, +2. Okay, so there's lots of things this one could do. Do you guys see the different things? So when I'm looking at it, I'm like, well, does it go up and then down? Oh, I don't know if it can go back up to that spot. I don't know what it's doing. Okay, so that's when end behavior is useful. Okay, so end behavior. It starts with x to the 4th, so it's positive, and it's even. So what's the most basic positive even one we have? Right, so it's going to look like y equals x squared. So the ends are going to look like that. Okay, so then I draw those on my graph. So I draw some ends. Okay, now can you tell what it looks like? It's going to come down, it's going to go through that point and back up. And those are the only places it can cross the x-axis. Those were the only zeros we had. It's going to go up and hit that point, back down. Looks like a W. Okay, last one. Okay, this one's a little harder. All right, so x-intercept, we plug in 0 for y, so I get 0 equals -x cubed plus x squared plus x minus 1. Okay, I'm going to have to split the middle. There's 4 terms. I don't like that negative, so I'm going to pull the negative out too. So I'm going to pull out a -x squared. When I do that, what's left in the parentheses? Santiago, what do I have left? Close. -1, right. All right, now I know I want an x minus 1 over here, which is what I already have, but you always need a placeholder. You always need to pull out a number and a sign. So I need to pull out a +1. See how the 1, if you multiplied it back in, you get that. So you always need a number and a placeholder. All right, so now I have my x minus 1 in common. So I pull it all the way to the front. So I have an x minus 1 out front. And then I have negative x squared plus 1. Okay, that negative x squared plus 1 is still annoying me. I don't like that. So what's something I can do to get rid of the negative? Pull it all the way out to the front. So I'm going to have a negative. The x minus 1 stays the same. And I basically pulled the negative out of the second part, so it's going to be x squared minus 1. Okay, that's a little bit easier to see how it factors. Or you could have written it as 1 minus x squared, too. So I have negative x minus 1 times x squared minus 1 is the difference of two squares, so it factors. So I get x plus 1 times x minus 1. So if I set each piece equal to 0, what about this negative? Does that matter? 0 equals -1? No, that doesn't give you any solution. So if I had 0 equals x minus 1, if I solve that, I get x equals 1. If I had 0 equals x plus 1, I solve it and get x equals -1. And the last one, I get x equals 1. Okay, this means that x equals 1 has what we call multiplicity 2. It was an answer twice, so we say it has multiplicity 2. So at this point, it looks like y equals x squared. Okay, so basically at that point, at 1, you're going to come in like this and hit 1 and go back up. Or it could look like y equals -x squared. So it could come up and hit the point and go back down. But basically it's going to hit the point and not go through the point. Okay, on all the other ones we had, they had multiplicity 1. They were an answer once. So that's why, see how it goes straight through like a line? It goes straight through that 0, straight through, straight through, straight through. Same with the other one. You went straight through the zeros. Okay, that's what it's telling you, the shape at the 0. Right, multiplicity 1 means it looks like y equals x. Y equals x the first. So multiplicity 2 means it looks like y equals x squared. So what if it was multiplicity 3? What if I had an answer 3 times? What does it look like? The snaky thing, y equals x cubed. So if I had an answer 3 times, it would come in, it would hit the 1, and then it would go through like the snaky thing. So it'd look like that. Make sense? Okay, so at 1, I know I'm going to look like some kind of parabola shape. Okay, I also have -1. My y-intercept, that one's easy. What's the y-intercept? -1. End behavior. It looks like -x cubed. So that means it's going to look like this on the ends. So I'm going to start at the top and then go to the bottom. The end behavior will help you remember about the multiplicity. Because see what happens as I go through? I'm coming down, I'm hitting the -1, I go through it, I go down to my y-intercept, I go back up, and then I'm like, oh, my end behavior means I'm going down. I can't go back through this. So do you guys see what happens there? You hit it and then go back down. And that's exactly what it should do. That's the multiplicity 2. Because it looks like a little parabola if you zoom in on that point. Okay?